Awesome. Hi, everyone. I guess I can actually take these off for the talk. Hi, everyone. My name is Martin Braun. I'm an Android developer for Stream, who are nice enough to have helped me be here today at the conference. So I want to give a quick shout out to our product, which is a chat SDK that's super easy to integrate on all platforms where you might need a chat function in your application. Including Android. It's also open source, and it does everything you could possibly desire from chat integrations. Let's get straight into the topic now, though. So today I get to talk about delightful delegate design, which really is one of my favorite talks to give. And let's jump straight into that. Whenever you're learning Kotlin and when you're working with Kotlin, you'll see that there are some features in there which look like deeply integrated special constructs in the language at first, but then it turns out that they're just clever uses of simpler, more basic constructs. For example, there's to, which is an easy way of creating pairs of objects, or there's with that lets you scope into a given object and run code as if you were inside the scope of that object. Or there's use, which is kind of Kotlin's replacement for Java's try with resources construct. And it will free up the resource that you've called it on after you have executed that block of code that you pass into it. And there's things like lazy, which will give you lazy initialization for a property, meaning that the property's value won't be created, it won't be initialized when the property itself is created. For example, if this property is inside of a class, then the property will not be initialized when the class itself is constructed, but instead it will only be initialized when you first access the value of the property, and it will be cached afterwards. So if we print the value of this pi property that I have here with some calculations that approximate the value of pi, you'll see that the first time around this takes a very long time because we have to run all of that code. But then the second time around, it will be quite fast because it's already cached and we are just reading a stored value. So this is the feature that I want to focus on today because this is implemented by delegates. Let's see what we would have to do if we didn't have delegates available to us. Here's a class where I store constants, and I have the same behavior implemented here without using this built-in lazy thing. The way that I did this is I have a private backing property, which stores null by default. And then I have the public API of the class, which is a non-nullable double property. And I've written a custom getter here, which checks if the backing property has been initialized. And if it's still null, then it runs all of those calculations to calculate the value of pi. It assigns the backing property and then returns its value. And if I wanted to have this same behavior for other values, other properties in this same class, I would end up duplicating a lot of this code. I would most likely actually copy paste the previous properties and then just rename the name of the properties and change the calculations. So I would be repeating the same pattern for each property that I want to have this same behavior: nullable backing property, custom getter, checking if it's initialized, and so on and so on. Lazy lets us do this easily, but lazy is not as built-in as it might seem at first. The only language feature that's at play here is property delegation, which is really just the by keyword. This is what tells the compiler that this property will not be implemented the usual way, where it might have a backing field and a getter or setter that's either generated or custom, but instead the property will be implemented by some sort of an object. Which contains its implementation. And on the right-hand side of the by keyword, you just have to create something that can act as a properties implementation, and everything else will work from there. We're going to recreate lazy to see how this works at basic level. And instead of going with that syntax, we're going to go for a simpler syntax first. We're going to create a class called lazy delegate and pass in the calculations to that class. This is how this class would have to look like. So as you can see, it's generic because we want to reuse this and not just use it for initializing doubles, but any kind of value lazily. And we are taking a function type as a parameter. It's important that we're not taking the already calculated value. We're just taking a piece of code as a parameter, which we will execute when we need it, but no earlier than that. Then for this class to be able to serve as a property delegate, we have to make it define a getValue method. And this getValue method by convention has this very specific signature. It has to be an operator, and it has to have these specific parameters, some of which we'll look at later. The important part is that it has to return something of type T. In this case, it has to return a double, because this is the function that will be called whenever you read the value of the property, which is pi in this example. Then we have to store state somewhere, and we don't get a backing field like inside custom getters and setters, but we are inside of a class. So for whatever state we need to hold, we can create properties in this class, and I'll just create a nullable property here again, which is null by default. And then inside the getter, the getValue function, I can check if this property already has a value. If not, I can run the initializer and assign the value and then return it. And with this class implementation, I really just replicated what I had before in a custom getter and setter and in a separate property, but it's now in a reusable class that we can delegate to whenever we need this behavior. And we could, of course, execute this and would see the same behavior as the standard library produces. We don't quite have the syntax of the standard library lazy solution, however. First of all, there are these parentheses here, which are extra compared to that. Because we didn't have to have those with the standard library lazy. So we can actually just drop these because we are calling a constructor here. And a constructor call is a function call after all, and trailing lambdas in function calls in Kotlin can be moved outside of the parentheses. So that's why we can drop these. And then the other improvement we would want to make is instead of naming our class, we would like to see the word lazy there as syntax, which would be the same as what the standard library has again. And there are a couple different approaches to getting to this syntax. The lazy way, pardon the pun, would be to just rename the class lowercase lazy. And this would get us to the syntax, but it breaks all kinds of conventions about naming Kotlin classes. So we would really rather not do this. Instead, we can keep the original name for the class and introduce a factory function that can create instances of this class for us. So this function is also generic. It takes the same initializer function that we require for the delegate and just creates an instance of the delegate for us. And it gives us this nice lean syntax. It's a good idea to use these factory functions in general. The standard library does the same thing internally. And you'll see that we make good use of these for our upcoming delegate implementations as well. It's also worth noting that while we re-implemented the basic behavior of lazy here, this is not as good as the standard libraries implementation. So you should probably still be using those and not re-implementing them. The standard library implementation, for example, handles threading. So it initializes the property in a thread-safe synchronized way by default, which you can also customize if you want. And it also allows you to initialize to a nullable value. Here we are using null to mark that the value doesn't exist yet. So if we were to initialize to a null value, that wouldn't really work because we would do that over and over again. The standard library allows you to do that as well. So you should use that built-in lazy instead of this one, but we learned a lot about delegates here. From here on, I would like to move on to Krate, which is a library that's based on Kotlin delegates, and it wraps Android's SharedPreferences APIs for you so that you can access things in there easier without having to go through its original APIs. And from here, we're going to look at some of the implementation in Krate and how it uses delegates to provide a really neat API. At the code level, Krate is an interface, and all that it contains is a single property, which is a SharedPreferences instance, which makes it very simple to use. There's also a default implementation of this called Simple Krate that ships with the library, and this lets you easily implement the interface. You just have to pass in a context to this class, and it will open the default SharedPreferences instance for that given context. From here, I'm going to split the slides in two. And on the bottom of the screen, we're going to keep implementing Krate. We're going to implement some of the delegates and functions that are in the library. While on the top of the slide, we're going to write some client code, which is in some different module and is being built on top of the Krate library. The usage that we want to eventually get to looks like this. So we want to be able to create our own Krate classes, for example, by just inheriting from simple Krate, which makes it faster because we just have to pass along that context. And then for each value that we want to store in shared preferences, we can list those as properties inside the class and delegate each of them into functions which are provided by the Krate library. And the magic of this really is that the syntax for accessing these properties stays the same as if they were real values in memory and not served by these delegates. So even though you are modifying values in shared preferences, all you would have to do is use the regular property access syntax, set a value to true, read the current value of a property, and so on. We're going to start with the basics and implement just one of these delegates, the one that stores ints. And again, just to emphasize this, the syntax we are going for will look like this, but under the hood, it will store this integer persistently in shared preferences. So we know that we're going to need a class for this, just like with our previous delegate. This time around, we're going to call it an int delegate, and it will take two parameters, the shared preferences to use for storage and the key that it should use to store our values for us. Inside this, we now have to implement two methods as we are implementing a var, which can both be read and written. So the getValue method is the same as before. This will be invoked when we read the value of the property. And then the setValue method is what will be executed when we store something in this property. This receives the new value as its last parameter. Inside these methods, the implementation is just calling into the shared preferences APIs. We are omitting some error handling and special cases here so that the code for the sake of the talk stays simpler, but you can go and check out Krate's implementation later on. It's open source and it's on GitHub. So this is what the simple implementation would look like. In getValue, we just grab the value with the given key from shared preferences, and setValue is just a bit more involved. We start editing these shared preferences, we place the value in there with the given key, and then finally we apply the changes. And with this, we have a working library implementation. We have a working basic API. We could delegate our score property in the client code to an int delegate and pass in the two required parameters. The shared preferences here is, of course, available to us because we are inside of a Krate. And remember, the only thing that exists on the Krate interface is this shared preferences property. We can make this nicer, however, by again going to a factory function. And this factory function is a bit special in that it's an extension on the Krate type. This gives us multiple useful things. For one, it will only be available when you are writing code inside of a Krate. This means that it doesn't pollute the global namespace. It won't show up in autocompletion results all over your project when you type in int. It will only show up if you are writing your code inside of a Krate. And the other benefit is that since this function is an extension on Krate, we can grab the shared preferences property from the interface, which means that when we call the function, we no longer need to pass in two parameters. We can just pass in the key that we want to use for storage, and everything else is taken care of under the hood. So now we have two APIs that are public in our library. Our clients could either use this nice new factory function that we've created, or they could still create instances of the int delegate class, which is more tedious to use and is really meant to be the private implementation details of the library. So we don't really want people to be calling this directly. We can solve for this by using visibility modifiers. We can use internal as the visibility for the implementation class. And this will make it so that it's only available within the same module, which in this case is Krate, the library module itself. And from here on out, it couldn't be referenced from client code, which is good. While we are at adding visibility modifiers, we can also add explicit modifiers for the other API, so all of our public API. And this is not a change logically, just on the code level, because every declaration in Kotlin is public by default. But by making it explicitly public, we are actually adhering to JetBrains' official recommendations for Kotlin libraries. This is in their style guide that API should be explicitly public. And you can probably see why that is. If you have explicit public modifiers, it will be easier for you to keep track of what's public in your library. So you won't accidentally modify these declarations, for example, and break client code. Also, if your code is open source, if someone is reading that code, they will be sure that you really meant to make that specific piece of API public. And they will also think that you're the kind of person who reads JetBrains' official coding conventions for libraries, which will probably also make you look good. There is a lot more to say about visibility in Kotlin libraries. So I've written an article about this, which I recommend that you check out after this talk. And please note that you don't have to take notes of all of the references along the way. There will be a very simple single link at the very end, which will point you to all of these. Getting back to our example, we have added these visibility modifiers and hidden the inDelegate class so that it's not used directly. However, we have also broken our project. At this point, this code would not compile. There would be an error right there on the factory function. And this error would be there because we are now exposing one of our internal types as the return type of a public function. So what we're saying there is that we want people to call this public function, but then they are not allowed to know the type that we are returning from it, which just plain doesn't make sense, so the compiler doesn't allow it. How could we solve this without exposing our internal class again? Well, we might come up with the solution where we would create a new interface. We would put the get value and set value methods into that interface. We would have our own delegate class implemented. And this interface could be public, so we could use this interface as the return type of the factory function. This would solve our issues pretty neatly. And the good news is that we don't even have to create this interface ourselves, because one of these interfaces ships in the Kotlin standard library, and it's called, very descriptively, read-write property. This contains exactly the two methods that I've just mentioned and what we've implemented inside our delegate class. So we can add the override modifiers here. And that's all we need to do to adapt to this interface. You might have noticed that there are two type parameters in the interface as well. The second one is self-explanatory. That's the type of the property that whatever implements the interface implements. And this is just int in our case. This has to match the return type of the getValue method and has to be the same as the type of the last parameter of the setValue method. However, there's also this other type parameter where I have already put in Krate. This parameter lets you restrict where your delegates might be used. In this case, by putting in Krate here, I'm saying that this delegate can only be inside of a class that is a Krate itself. And if you look at the declaration of the interface we are implementing, you'll see that these first parameters in each of the functions have to match the type that you have put in there as a generic type parameter, because these thisref parameters will actually be the current instance of the class that contains your delegate. So in our current example, these thisref parameters will always point to the instance of my Krate that this int delegate is being used in. This means that we now have reference to the Krate itself inside both of our methods. So we can actually use that to grab the SharedPreferences instance, and we no longer have to pass that in through the constructor parameter. Finally, we would, of course, want to update the factory function, which is still broken at this point, to make it return this interface, which is a great type to return from public API in a library, because it is a type that's already there in everyone's projects. It's in the standard library, and it's very descriptive. It tells you that this is a property. It can be read and written, so it can be used as a var. And you can also only use this in crates, and it is a property of type int. So it really describes everything about our delegate that we created. As a bonus, if you have trouble remembering the exact signatures of the getValue and setValue methods, which would be very understandable because they are not trivial signatures, it's good to use the interface when you are implementing delegates, because if you make your class implement the interface, and you can probably remember the name of this interface, then you can use the IDE to generate both of these methods that you have to override, so that you don't have to write down the signatures yourself or copy it from the Kotlin documentation or anything like that. All right, we're done with a simple implementation there. So we have implemented storing ints in shared preferences and wrapping all of this using delegates. But what about types that shared preferences doesn't support? We could copy the previous implementation for Booleans and strings and so on. We would just have to change some types around and some names around. But people might also want to store values in Krate, which are not these basic types that shared preferences supports. For example, what if you want to store a list of users in a Krate, such as this? First of all, this is not the best idea. Please remember that Krate is just a wrapper around shared preferences, and it's not generally the best idea to store complex custom objects in there. The common way to do this is by serializing things into strings, so storing them as JSON, for example. But there are a lot of cases where you really should be using databases instead. However, this was a feature request, and there are legitimate cases where it's better or at least easier to store these things in shared preferences. So Krate has decided to support this. And the initial support for this was JSON based. So there is a JSON pref which ships in a separate artifact that you can use to serialize values using JSON and store them in Krate like that. Note that this is just the first library that Krate supported, because it was the most requested one, because it's quite popular, unfortunately, because in Kotlin, using JSON is not a very good idea. I would recommend using something like Moshi or Kotlin X serialization instead. For Moshi, Krate actually has dedicated support too. But we're going to look at JSON today, because there's a lot to learn here from the implementation of the delegate. I'll simplify the code a bit. Instead of going for a var, we're just going to do a val. So we're going to do a read-only property here, because all of the interesting code will be in the getter of the delegate. And so we'll just skip implementing the setter for now. Of course, you would ideally implement this in a real implementation as well. So we're going to immediately apply everything that we know from our previous delegate implementations. We are creating a class called JSON delegate here. It's generic, it's internal, because this is going to be implementation detail. We are making it implement an interface. This time around, we are using another standard library interface, which is read-only property. This is the same as the previous one, but it only has the getValue method in it. So it can only be used for read-only val properties and not for vars. Inside the getValue method, we are fetching a string from shared preferences with the given key, and then we are using the JSON APIs to create an instance of whatever type we are storing here. We are parsing the string into type T, and we are using the JSON type token for this. And of course, we are also adding a factory function, which is called JSON pref here. It's also an extension on Krate. It's also generic. And it returns the interface type while creating instances of the internal class internally, well, inside it. And this looks like a correct implementation. If we had the setValue method here with its implementation too, then we would be able to write values into shared preferences. We could store a list of users. It would really be converted into JSON and stored as a string in shared prefs. However, there is a bug here, which would be apparent when you start reading those values back, parsing the strings back into JSON. And the bug is related to how we're telling JSON to deserialize from a string. So what we want to tell JSON is, for example, with the client code that we have here, is to deconstruct the string into a list of users. But we are doing this by using generics and the type token. And so what we're telling JSON here is to create something of type T from the given string. And type erasure will kick in, which is a feature or more like a trait of the JVM And what it means is that the concrete types, so the concrete substitution for this generic type parameter t, will not be available for us at runtime. You can think of type erasure as just replacing all usages of type parameters with the Java object type. So by the time that we get to runtime, what we're telling JSON, instead of please give us a list of users, is just please give us an object from this string. And unfortunately, JSON is not very type safe, and it will not produce any warnings about this, but it will really just try its best to give us any object, any arbitrary object that represents our string. And it will, of course, not decide to create instances of our custom user class or anything like that. It will use a very general representation of using lists as JSON lists and hash maps as JSON objects, and just nest those into each other. So whenever we try using these objects as a user and try accessing properties on there, we're going to get runtime crashes, which is not the ideal experience. So how can we fix this? How can we get this type information back at runtime if type erasure gets rid of all of that typing? Turns out that Kotlin has a feature exactly for this, which is reified generics. We can make a type parameter reified to have its concrete value available at runtime, but we can only do this for functions. We can't do it for the type parameter that we have in our class. It only works in functions, and it only works in inline functions, which is why I've added the inline keyword as well. And pretending for a moment that this works, and we'll look at how it works in a moment. So pretending that this works, we could now create the type token inside the factory function out there. Here, we supposedly still have the real type available in the type parameter t, and then pass this in as a constructor parameter to the delegate class, so that it now uses the correct type for JSON serialization. So why does this work? What's reified, and why do we have to inline our function for this? Well, inlining functions means that whenever someone calls that given function, there will not be a real function call there at runtime. Instead, at compile time, we are replacing the function that has to be inlined with the body of that function. So here, the call to the JSONPref function is replaced by the body, which is the just the constructor call. And we also substitute all of the parameters in here. So first, we substitute the key, which was just a string that was being passed in. And we also substitute type parameters. So here in the bytecode, we are going to end up with a type token of list of users instead of a type token of t. And this means that this code is actually no longer generic in the bytecode. It's referring to a concrete type, which will be available at runtime and will create the correct type token, which is just what we wanted. So we have solved the serialization issue. We would now be able to write values into shared preferences and read them back as well, and everything would be going through JSON. We have one last issue to solve here, which is that this code, again, would just not compile in its current state. And the error that we would get now is related to inlining. So we've seen that inlining places everything in the body of an inline function to the call site. And we now refer to an internal type in our inline function, which means that our client's bytecode would end up containing a reference to something that's internal in our library. This, again, would be breaking module boundaries and access restrictions. So the compiler doesn't allow this. Luckily for us, there is, again, a specific Kotlin feature which is meant for this exact situation as a solution, and that's the published API annotation. What published API does is that it will let you use that internal type that you've annotated with it in public inline functions. It's very specifically meant for this use case. So this type will now be available in inline functions, and your clients will really end up referring to your internal types inside their compiled output, but they will still not be able to access the declaration that's internal at the source level. So they can use the JSON-pref function, and we'll see this type in their bytecode if they take a look at it, but they can still not write source code that would create instances of JSON delegate by hand. It won't be there in auto-completion results, and so on. Of course, if you do this, you have to keep in mind that making changes to an internal type, if it's marked with published API, might break existing client code if it's not recompiled. So from here, you have to treat this declaration as effectively public. And if you break it, you're going to break binary compatibility. Again, there's a lot more to say about source and binary compatibility. So I have this extracted into another article, which you can go and read after this talk. To wrap things up, I would like to look at Krate's API. This is the sample that I've shown you at the beginning, which is what we wanted to achieve while implementing things. But this is actually not Krate's real API. The real API is just a tiny bit more complicated than this. So in the real API, there are two variants of each of the delegate functions. One of them takes a default value as an additional parameter next to the key. And this default value will be used if you read the value of the property before writing something into it. And if you use these two parameter delegate functions, you'll get non-nullable values, so a regular Boolean or a regular int value. But there is also still a single parameter delegate function. But in this case, we can't guarantee that there's a value to read if you haven't written something into that property yet. So these properties will return null by default, which means that the properties will have nullable types. So you'll have to do null handling on them. You're free to decide which approach you want to take for each of your properties. And then to really wrap this up, I just want to show you one neat way of using Krate if you have dependency injection set up in your apps. So our recommended way of using this is to create an interface which contains all of the values that you want to store in shared preferences. You can then make your Krates implement this interface. You can also have multiple Krates and multiple interfaces like this. And each of the properties can be implemented by delegating them into Krates functions. And from here, you can make the Krate object injectable. You are probably already providing a context somewhere in your DI setup. And you can bind the concrete Krate class as the implementation of this interface. So whenever you need to access these properties, you can inject the interface type and read and write all of them through that interface and not even have to think about how this is implemented under the hood. So in this case, you can just create an implementation detail even within your own applications. Plus, having these interfaces also makes it very easy to mock the behavior. It's super easy to create mock versions of these interfaces. And finally, I would like to point you to some references. So of course, I would be very happy if you checked out the library itself. Please try it, use it, start it on GitHub. Give us feedback about what's working for you in it and what's not. I'm happy to hear from anyone who's using the library, because I don't hear from people that much, but I know that they are out there and using it. Then there is a written version of this very talk, which contains nearly the same information that you can check out and also share with other people if you don't want to share a talk recording. And then there are all of the links that I was showing along the talk, and also some extra things about library development and APIs in Kotlin. Please note that I'm talking a lot about libraries here, but if you're working on a multi-module project, then each of those is really a library which has its own API, and you should really follow these same practices for each of those modules as you would follow for a public library, because it will help you a lot in the long run. So all of this advice really applies to anyone who works on multi-module projects as well. And with that, this really is a wrap. So here I have the final link where you can go to my website's talks page. There you can grab all of the slides as well as the references that I've listed. And if you're into Twitter and that sort of thing, you can also find me and follow me there. I tend to post Android and Kotlin stuff, as you would expect. And with that, we are pretty much done. And I have no idea if we have any questions, but we can go and see about that. Awesome. So the first question is, since we talked about inline and reified, can we also talk about what cross-inline does? I am not going to be able to explain that without using slides for it, at least not properly, because it's kind of a complicated topic. Cross-inline is a modifier that you can put on functions that you use inside inline functions. So parameters of inline functions that are functions themselves. And if you mark something with cross-inline, then you will prevent non-local returns from that function. I think that's the word to look up if you want to learn about cross-inline. The official documentation covers it pretty well. So just Google non-local returns in Kotlin, and that should point you the right way. Looks to me like that was possibly our only question. We do still have a couple minutes, so I'll stick around for like a minute more and see if any other questions land. Okay, I'll take that as no questions. If you do have questions later, you can reach me again on Twitter. That's probably the best place. You can also, of course, find me on the conference platform and just direct message me there. And thank you again for attending this talk. Have a nice conference.